So in this example problem, we're given a state of stress in the XYZ coordinate system, and we're asked to determine what would be the state of stress in the x prime, y prime, and z prime coordinate system. So we're given that um, that the system of is rotated 2 times. So we go from the XYZ coordinate system to the x1, y1, z1 coordinate system after due to the first rotation. So and then um, the second rotation is we go from the um, x one, y1, z1 coordinate system to the x prime, y prime, and z prime coordinate system. Okay, so for the first rotation, we're rotating about the z-axis 45 degrees clockwise, and then the second rotation, we're rotating 30 degrees about the um, x1 axis or the x prime axis. Okay, so what we're going to do here is we're going to set up a transformation matrix for both the first rotation and the second rotation. Okay? So if you recall, our transformation matrix is going to be equal to the so what we're doing here is we're going from, we'll do our first rotation, so we have x1, y1, and z1 is going to be equal to the projection from the original x, y, and z axis. Okay, so if we look at our coordinate system here, for if we look at if we draw a right triangle from our x prime and y prime axis, from our x1 axis, from our x-axis, if we draw a right triangle, what we'll see is that if we treat the x-axis as being the hypotenuse of our triangle, the cosine of 45 degrees would be, or the cosine of theta would give us the projection of x along x1. So we're going to write this as being cosine of theta. For the second, for the projection, if we do the same thing along y1 here, this angle here is going to be equal to 90 minus theta. Alright, and if we take the cosine of if we take the cosine of 90 minus theta and multiply that by y, the vector y along y, we would get the projection of y onto x1. Alright, and then our last one is going to be the cosine due to the projection of z along x1. And now z is it's drawn coming out of the page here. This is what z is going, and this is where z1 is going, and that's going to be 9. No matter everything in the xy or the x prime y x1 y1 plane will be perpendicular to that, so it's going to be 90. It's 90 degrees apart. So we're going to write as the cosine of 90 degrees. Okay. In a similar process, we can do the same thing for the y-axis here. So if we look at the y-axis, what we'll see is the projection onto the y1 axis from x is going to be going along the is going to be equal to the sine of 45 degrees, or you could think of it as being, if you use this internal angle here, this is equal to 90 minus theta. So we can say this is going to be equal to cosine of 90 minus theta. And what you'll notice is that the arrow is going along the opposite direction as y1, so we're going to include a negative sign here. All right. In a similar process, if we look at the vector y, its projection along the y-axis would be equal to cosine of theta. here. All right, times y, and then the last section would be again for the z projection onto y1. So in this case, it would be equal to the cosine of 90 degrees again. All right. Now we can repeat this process for the uh, z-axis, or the projection of the x, y, and z onto the z1 axis. So for x and y, those are both 90 degrees apart from z1. So we can write this as being equal to the cosine of 90 degrees, the cosine of 90 degrees. And then z1 is parallel with z, so that would be the angle between those would be 0. So this would be cosine of 0. Okay? All right. So if we simplify this all down, we know that the cosine of 90 minus theta is just equal to the sine of theta. All right. And so what we end up getting here is we'll get the first row will be equal to cosine theta, sine of theta. Cosine of 90 degrees is the same thing as 0. The second row will be minus sine theta, cosine theta, 0. And then the last row will be equal to 0, 0, and 1. All right. So this would be our transformation matrix for our first rotation. So we'll call this T1. Okay. So our second rotation here. Okay. So for our second rotation, we're going from the x1, y1, z1 coordinate system to the x prime, y prime, z prime coordinate system. Okay. So again, what we'll do is we'll have a transformation matrix where we'll have our new coordinate system, our x prime, y prime, z prime coordinate system that will get transformed to our new coordinate system using a transformation matrix and multiplied by uh, our old coordinate system x1, y1, and z1. So we're going to again have our directional cosines that we have to define here. So we're going to go, what is the, so for the case of relating x prime to x1, y1, and z1, what we'll notice is that x1 and x prime go along the same axis, so the angle between them would be equal to 0. So our directional cosine would be equal to the cosine of 0 degrees. Both y1 and z1 are 90 degrees apart from x prime, so therefore the angle between them would be 90 degrees, and then therefore directional cosines would be equal to 90 degrees. For our second case would be for the projections of x1, y1, and z1 along y prime. So for the first one is the projection of x1 onto y prime. Since x1 is 90 degrees from y prime, we could say that the projection would be equal to 0 because it's going in a perpendicular direction, and the angle is perpendicular, and so we can say that would be equal to the cosine of 90 degrees. Y1 is going to be equal to the projection of y1 onto y prime would be equal to y1 times the cosine of 30 degrees, or cosine of phi. Okay, and then our second, like the of y prime of z1 onto y prime, we can draw our additional triangle here. All right, and that would be equal to the cosine of 90 minus phi, or theta, phi here. All right, so for our last case here, we have the projection of x1, y1, and z1 onto z prime. So that what we'll end up getting is we'll get for z1 onto due to x1, again we would have cosine of 90 degrees since z prime and x1 are 90 degrees apart. The cosine or the projection of y1 onto z prime would be equal to negative. So this angle here is 90 minus phi. So it'd be equal to cosine of 90 minus phi. And then our last one would be the projection of z1 along z prime. So that would be equal to just cosine of phi here. All right. So if we simplify this all down, all right, this is the same matrix here, the same column vector here, and then we can simplify our transformation matrix as in terms of just sines and cosines and zeros. So we get the first row of our transformation matrix is going to be equal to 1, and then the second 1, 0, 0. The second row is going to be equal to 0 cosine phi sine phi. The last row is going to be equal to 0 minus sine phi cosine phi. All right. So we already know that from earlier we had defined that x1, y1, and z1 was equal to from above here. We had that x1, y1, and z1 was equal to the transformation matrix T1 times x, y, z. So if we plug in this substitution here, what we end up getting is we get x prime, y prime, and z prime is equal to T2, which is the transformation matrix to get from the x prime, y prime, and z prime to x1, y1, and z1 state, times the T1 times x, y, and z. So we're gonna. Right. So now we have our transformation matrix defined. So what we can then do is we can multiply these two together. So what we'll end up, if we multiply T1 and T2 together, what we'll end up getting is that x prime, y prime, and z prime are equal to our global transformation matrix, which we'll just call T. All right, and then times x, y, and z. All right, so if we multiply T2 times T1, what we end up getting for our values is we get cosine theta, sine of theta, and 0 for our first row. Our second row is going to be equal to minus sine theta cosine phi. The second row, second column would be cosine theta cosine phi. Our third row is going to be sine of phi. And then the last row is going to be sine of theta cosine, sine of theta sine phi. Minus cosine theta sine phi. And the last one is cosine phi. Okay, so that's our global transformation matrix. Once we have that defined, we can go ahead and we can use our our equation. So we know that our new state of stress x prime, y prime, z prime is equal to the transformation matrix times the original state of stress in the yz coordinate system times the transformation matrix transposed. If we did all of that work, we plug in our original values for theta as being equal to 45 degrees and phi as being equal to 30 degrees. What we'll end up getting is we'll get we'll end up getting sigma x prime y prime z prime will be equal to the following stress matrix. All right, so I'm going to pause the video for a second and just copy down the values so you can have them. All right, so this is our final stress matrix here in our new x prime y prime coordinate system. So again, in order to do a stress transformation, but you need to know the relationship between the new coordinate system, the old coordinate system, the x, y, z coordinate system, and your final coordinate system, which in this case was the x prime, y prime, z prime coordinate system. So in order to establish that, we had to use a set of transformation matrices, which were filled with our directional cosines to define the relationship between the xyz coordinate system and then our intermediate coordinate system x1, y1, and z1. And we did the same thing to go from our intermediate coordinate system x1, y1, and z1 to our final coordinate system x prime, y prime, and z prime. We could then substitute in our initial coordinate system transformation to the intermediate coordinate system to get a single transformation matrix that we could use to then transform our stress from the x prime, y prime, z prime coordinate system to the from the x, y, z coordinate system to the x prime, y prime, and z prime coordinate system. Right. So that concludes this video on stress transformations in 3 dimensions.